I welcome you all to this video tutorial, and in this video tutorial we'll go through few problems on maximum entropy, source efficiency as well as source redundancy. Then we'll continue our discussion with extension of zero memory source, where we'll derive a formula for source extension. I'm your Benak Patel, and let's get started. In our previous class, we have seen formula for upper bound for entropy. In a similar way, we did also went through the formula for source efficiency, followed by formula for source redundancy. So now let's solve some problems on these. So they have given a system that which is emitting one of three symbols. It can emit either A, B and C with respective probabilities 0.7, 0.15 and 0.15. So these are the probabilities that which are associated with symbol A, B and C respectively, and they are asking us to calculate its efficiency and redundancy. So this is the problem statement, and now let's make use of our known formula and try to solve this problem. So what all formulas do we know? We know how exactly source entropy is given, that which is denoted by H of S summation I starting from 1 to m pi log to the base 2 1 by pi. So this is the formula for entropy of a source, and we do also know upper bound for entropy, that which is given as H of S max in turn equal to log to the base 2 of n, where n is the number of symbols that which a source can emit. In a similar way, we do also know formula for source efficiency, that which is given as neta s equal to H of S divided by H of S max into 100%. We do also know one more formula, that is source redundancy, that which is represented with capital R, that which is equal to 1 minus neta s, that is source efficiency. This entire thing into 100. So now they have given three symbols, symbol A, B and C, and their respective symbol probabilities 0.7, 0.15 and 0.15 again, and they are asking us to find out source efficiency followed by source redundancy. Now, if I look at the formula of source efficiency, it has H of S in it as well as H of S max. So thereby, it's very important to find out both these values. So in an approach to find out source efficiency, because source efficiency involves H of S and H of S max, let's make use of our formula number 1 and formula number 2 in order to find out H of S and H of S max. So now what is this H of S equal to? So by formula we already know that it's I starting from 1 to m pi log to the base 2 1 by pi, and here what is the value for m? Value for m is 3, because I am having 3 unique symbols. So my formula would be I starting from 1 to 3 pi log to the base 2 1 by pi. So here if I expand the summation, I'll be getting it as 0.7 log to the base 2 1 by 0.7 plus 0.15 log to the base 2 1 by 0.15, and because symbol C is also associated with probability value 0.15, what I'll do is I'll try to simplify my step and I'll write it as 2 times. So this will be our formula when expanded. So if I calculate all these values, I'll end up with a value that which is equal to 1.1812 bits per symbol. So I recommend you to make use of your calculators and try to solve and try to get this value. So after finding H of S, let's find out H of S max, and in order to find out H of S max, we already know the formula, that which is equal to log to the base 2 of n, where n is the number of symbols. So here the number of symbols that I can have is A, B and C. So thereby the value for n is equal to 3. So in turn I'll end up with the value that is equal to 1.5849 bits per symbol. So this is H of S max, and I can easily find out my source efficiency by taking ratio of H of S to H of S max. So H of S is 1.1812 whole divided by 1.5849. I'll end up with the value 0.745, and because I need to put it in terms of percentage, I'll multiply it with 100%. So when I do so, I'll be getting 74.5%. So this is the value for source efficiency. In a similar way, the value for redundancy, I'll get it as equal to 1 minus neta s. So if I substitute the value for neta s, I'll be getting 1 minus 0.745. This entire thing should be multiplied with 100% because we usually put source efficiency as well as source redundancy in terms of percentage. So I'll be getting this as equal to 25.48, such that just by looking at these values, I can make out the efficiency of the source, that which is emitting three symbols A, B and C, and this source is associated with redundancy, that which is equal to 25.48. So this was our problem number 1. Now let's take up our second problem, that which says a certain digital frame consists of 15 fields. The first and the last field of each frame are same. The remaining 13 fields can be any of the 16 symbols with equal probabilities, and they are asking us to find out average information conveyed by the frame, and they are asking also us to find out average rate of information, that which is represented as capital RS, if 100 frames are transmitted every second. So this is our next problem statement. So before we start to solve this problem, let's go through this problem statement again. So they are telling that there is a certain digital frame consisting of 15 fields. So there is a digital frame that which is consisting of 15 fields. Field number 1, 2, likewise 14 and 15. So I can think of this as a digital frame. So each of these fields are separate. Over here, field number 1 and 15 are same for all the frames, and the remaining 13 fields can be filled by any of the 16 symbols. On a whole, this is a size of 15 field. If I subtract 2 with 15, I'll be getting 13. So I'll have 13 remaining fields, and each of these fields can have any of the 16 symbols. Source alphabet M containing 16 symbols like S0, S1 till S15. So I can have this field 2 containing any of the 16 symbols. So now they are asking us to find the average information conveyed by the frame. So average information is nothing but entropy, that which is represented as H of S. So initially they are asking us to find out H of S, followed by to find out average information rate, that is capital R, if 100 frames are transmitted every second. Now over here, I can think of this H of S as cumulative kind of entropy due to field number 1, field number 2, field number 3, likewise field number 4, field number 13, field number 14 and field number 15. So I can think of this as H of S being equal to H1, where H1 is entropy due to field number 1 in a single digital frame, plus H2, that is entropy due to second field in a digital frame, plus likewise H14 can be thought of as entropy due to field number 14, and finally H15, that is entropy due to field number 15 of a single digital frame. Now if I read out this problem statement again, they are specifying that first and the last field of each frame are same. So here first field and field number 15 are same for each digital frame, and hence because they are same, they are not changing their values. So thereby this is a known fact that these two fields will not change their value, and because they are not changing their value, there is no curiosity involved. When there is no curiosity involved, the information conveyed by this will be equal to 0, and because the information conveyed by these two fields are equal to 0, what I can think is, out of this H of S expression, H1 as well as H15 are straight away equal to 0. So this entropy, overall entropy, is contributed only by these 13 fields that can have any of these 16 symbols in them, and hence we are supposed to calculate entropy only due to these 13 field values. And if we clearly see this, these fields can carry any of these 16 symbols, and hence all these digital fields are having equally likely probability. Here they are also specifying that 16 symbols with equal probabilities, and hence I can think of H of 2 being equal to H of 3, in turn being equal to H of 4, likewise H of 13 being equal to till H of 14. So all I got to do is find out only one value, and I got to multiply it with 13. So thereby I can find out the overall value of entropy. If I try to find out entropy due to just field number 2, I can have it as equal to log to the base 2 n. So here I am making use of this formula because each of these fields can have any of the 16 symbols with equal probabilities. When I am having equal probability distribution, then all these H are equal to h of s max, and by now we already know the value for h of s max, mathematically given as log to the base 2 of n, where n over here can be thought of as number of symbols, and there are 16 symbols. So if I substitute 16 in the place of n, and I can rewrite this 16 as 4 square, and 4 in turn can be rewritten as 2 square. So in fact, I'll have this as 2 power 4. And in fact, I can make this part to jump onto the front, and log to the base 2 of 2 is equal to 1. So all these entropies are equal to 4 bits per. So here I'll not make use of the term symbol, but instead of symbol, I'll make use of the term field, because here we have considered digital frame where each of these are digital fields. So it's 4 bits per field. I'll make use of this formula again back here, and by now we already know that h1 as well as h15 are equal to 0, and remaining h over here, they're all are having equal values. So I'll make use of only one h over here, and I'll just multiply it with 13. So h2 value over here is 4 bits per field. So in fact, I'll get it as 4 times 13, and 4 times 13 is 52 bits per. So now I'll change this field to frame, because when all these individual 13 fields along with field number 1 and field number 15 will make up a frame, and here down here, because I have multiplied this individual field value with 13 times, in turn I'll be getting it for a single frame. So overall entropy value will be 52 bits per frame. Now let's try to calculate the value for average information rate, capital R, and this average information rate R is given as equal to h of s into rs, where rs is equal to 100 frames every second, and in fact I can make out average rate of information R equal to h of s value is 52 bits per frame, and this value is 100 frame per second. Here I can cancel out frame on the denominator as well as on the numerator, and I'll be left out with 52 times 100. I'll be getting 5200 bits per second. So this is the average rate of information if we are having 100 frames getting transmitted every second. So if I think of source emitting frame 1, frame 2, likewise frame 100 every second. For 1 second, I am getting 100 frames being emitted, and we all know the frame structure of each frame over here, that which consists of 15 fields, field 1, 2 till 15, where these two fields are common for each frame. So this average rate of information gives us an idea of how many bits are being transmitted per second.